Sorry, just plug in my presenter. Okay. All right, abstractions. So numbers are abstractions. You can't just point to the number 3. You can only point to 3 somethings, like 3 bicycles, or 3 sheep, or 3 examples on a screen. You can represent 3 in a number of different ways, and this was just a result of me searching for 3 in the Unicode standard, and it's only a selection of them. And you can concretize numbers in a number of different ways. For instance, a length, a weight, or a speed, or a temperature. But in the end, these are all the same versions. These are all the same 3s. There is only one 3, but it's in our heads rather than in the world. Now, data is an abstraction as well. It doesn't really matter how you represent it in the computer. You've got one abstraction, for instance, 20 degrees Celsius, and then you can represent that in different ways in different representation languages. But in the end, those representations all represent the same abstraction. And it's worth noting that HTTP recognizes this too, because a URL represents a single resource, a single abstraction, and then uses content negotiation to select a particular representation of that resource. So ixml at its base is all about that. It takes a representation of data, typically with implicit structure. It uses a description of the format of that data in order to recognize the data structure. It creates, as a result, a representation first internally with explicit structure of the data, and then you can do anything you want with that structure. For instance, you can serialize it as XML. Some representations in the world are weaker than others. They may not be able to faithfully represent all the abstraction, and therefore they're not reversible. XML is probably the best available representation we have, generic notation for generating representations, I should say. So the intention behind ixml, invisible XML, is to allow extracting abstractions from representations, converting weaker representations into stronger ones, in other words, explicitly structured ones, and therefore XML is an excellent target for those representations. So this is the processing step, the basic processing step for ixml. What you've got is a textual document with a description of that format. The processor then takes those 2 things and generates a structured version of the document. So the square things are textual documents. Triangular things are some structured representation of data. So in these 2 things are the same abstraction, as it were, just in 2 different representations. Now you'll notice the description there is in a triangle, in other words, in a structured version. But normally you supply that description in ixml, which is a textual document describing the format of the document. So in fact, there's another step involved. Here you have the description, and it takes the format of ixml, it converts it then into the same description but then structured, which is then used for converting the document into its structured version. So this is the whole process, and of course to get that initial structured version of the ixml language, you have to go through a bootstrap phase in the first place. So in fact, these 2 together is the normal operation of ixml. It takes the description, structures it, as it were. It takes the document and uses that structured description to turn it into a structured document. So I'm going to very briefly talk about how ixml looks and how you define the format of a language. So for instance, and I'm going to use here a programming language. Let's just assume we're trying to define a simple programming language. So it consists of a number of rules, and a rule consists of a name and then a number of alternatives for that thing separated by semicolons. Alternatives are just a sequence of items, 0 or more terminals and non-terminals separated by commas. So, for instance, an assignment is an identifier followed by colon equals, literally followed by an expression, whatever an expression is. And then what happens is that input is taken, and any input that matches that grammar is parsed into a parse-tree, which is then serialized as XML. So if you've got some definition of your language, and you've got input I becomes 0, then you would get output that says, this is a statement, it's an assignment, it contains an identifier I, colon equals an expression, which is a number 0. By default, and this is important for later in the talk, all input characters end up in the output. So all that we've done is inserted elements, or tags rather, around the input to show you what the structure of the input is. Now you can control your serialization by adding marks to the IXML definition. So for instance, if I put an @ sign before the ID, I'd be saying that I want that thing to be serialized as an attribute on the element. So then I would get assign ID equals I, and then the rest just the same as the first time round, the expression. You can also mark things to be deleted from the output. So for instance, if I'd put a minus before the colon equals, then it just doesn't turn up in the output. And similarly, you can do that for non-terminals, for instance, expression. If I put a minus before that, then the tags for the expression don't appear in the output, but you still get its element content. If you know IXML already, you'll be, here's something that's new in the new version, that you can actually also add things to the output that aren't in the input. So this isn't a particularly useful example, but for instance here, this adds a semicolon into the output, into the text of the output. There are more useful use cases, but this is just to show it working. Now there's much more, and you have two options. You can either go and read the specification. The slides are online. You should be able to find them easily enough, or otherwise you can go to the tutorial, which is also online, or tomorrow I'm giving a tutorial and you can just come to it. But you've seen the essence, and that's all you need for the time being for this talk. So here's just an example in use, actually, for this conference. The one thing that I really loathe about producing a docbook for the conference is the damned bibliography, which I struggle to get right. And so I just wrote an IXML grammar for the bibliography for this conference. And so, for instance, I now have a textual line that has the abbreviation spec, author's name, who's an editor, the title, the publisher, the year, and a URL. And so the IXML grammar, which I use to process this, says a bibliography is one or more biblio-entry values. A biblio-entry consists of an abbreviation and either an author or an editor, a comma which gets deleted, a title, a comma that gets deleted, a publisher, a comma that gets deleted, publication date, a comma that gets deleted, and then optional page numbers, and then 0 or more biblio-miscs, which are URLs, or biblio-IDs, which are ISBNs and DOIs, and so on. And so running that through this, I get my biblio entry for the conference, which made my life very, very much easier. So anyway, I'm here to talk something about the implementation. So the IXML is actually a grammar. And so you use a parsing algorithm to take that grammar and the input and turn it into the output. Now, there are many known, very, very many known parsing algorithms, and most of them have restrictions on the languages that you can define or process. Now, we didn't want those restrictions, so IXML requires implementations to use a general parsing algorithm, of which there are a handful, that doesn't add any extra restrictions. So the pilot implementation that I wrote uses early, which was one of the earliest and best known of the general parsing algorithms. And as I've described in an earlier paper, you can see it as a pseudo-parallel parsing algorithm. What happens is that when you're parsing a rule like sentence is A or B or C, it splits into 3 parallel subparsers, all starting at the same point in the input, one for each of those alternatives. And if a subparse fails, it just terminates and doesn't do anything. But if it succeeds, it records its sub-parse-trees and terminates. So at the end of the parsing, what remains is a sort of parse forest of lots of these little sub-parse-trees. And so the first thing you have to do is to see whether the parse was successful by looking to see if the root node of the grammar has a parse that covers all of the input. And if it does, then you can go on to serialization. Serialization just does a tree walk over those parse trees. Non-deleted terminals then just get serialized to XML elements. Deleted non-terminals just have their children serialized, so it doesn't produce any element tags. And non-deleted terminals and insertions are just output into the serialization. There's a bit of extra work for attributes because they become before the element content. And so for non-deleted terminals, you have to do one subwalk, and it's only a very short one actually, for the attributes, and then one for the main content of the element, which is down the whole tree. There's one quirk. Because of element deletions, here this example, for instance, a sign is a target, and a target is an attribute ID. Target has been deleted, so there's no element to put the attribute on. So it has to actually be walked up one level and end up on the assign. So that complicates very slightly the tree walk for elements because you have to go down deeper through deleted elements to see if there are attributes that have to be on the higher level element. The parse may have been ambiguous. The classic example, time flies like an arrow, fruit flies like a banana. So the same string can be regarded in 2 different ways or more. The serialization tree that walk doesn't matter. It just finds one parse and then just serializes that. But of course, you as user of the output, it's important to know that this was only one possible structuring of the data that you got. And so IXML requires, on the top level element of the serialization, IXML state is ambiguous, just so that looking at the output, you know that there were other possible interpretations. This, to get this, it's a very simple extra tree walk just to see if there is any root from the top node that's ambiguous. So the pilot implementation I wrote actually to support the development of the language because it's been changing over the period of development as it's been tested on users and generally been made better. So it was there to try out different approaches and find different solutions to the problems. And of course, to generate example outputs for the papers that I wrote about it. So my primary aim in writing it was speed of implementation, flexibility so that I could change it quickly. And I wasn't interested in creating an industrial strength top speed implementation. That could come later. So it's actually written in an interpreted language with very high-level data types, ABC, which was the predecessor of Python. It's about 500 lines of code for the bootstrap parser and 700 for the full processor. So now to talk about future work of the implementation. So in this diagram, you can see the description gets turned into a structured output, and the suggestion was that that's always XML. But in fact, the parser just needs the structure that it needs to describe a grammar. So one thing you can do is actually serialize straight into memory rather than into XML serialize it directly into the form necessary for the parser, so into the internal form. So this allows for some simplifications because an ixml parse will never be ambiguous, so you don't have to do certain sub-steps of the serialization. And of course, it speeds it up since it eliminates one whole parsing phase. So that's some future work. Another thing that I want to investigate is the possibility of round tripping. That is, you've got your your input format, you've produced a structured representation of that, but it will be interesting to see to what extent can you get the original form back having done that parse. Now, in the very simple case, where you haven't got any deletions or attributes or anything, then it's just trivial, because all you have to do is concatenate the element contents, and you've got the original form back. And even with element deletions, there's still no problem there, because you haven't deleted any characters, you've only deleted elements. So it's still simple. The problem comes if there are terminal deletions, where you've deleted characters from the input that haven't turned up in the output. How do you get those back? And in the general case, the only way to deal with this is to parse the output back using the same grammar. And I'm going to show you what that involves, and it's actually quite an interesting problem. So what you need is actually a parser. It's very similar to earlier. You can just use an early parser, but with a different way of handling its input, in order to discover which characters have been deleted so that you can put them back in. So you're parsing the parse tree, in other words. So for instance, if you've got something that's been parsed as a statement, then to parse this parse tree, to go back, then you're going to expect the tag statement to start off with. Then you split off 4 subparsers in exactly the same way to do the other bits, which may fail or succeed. And then at the end, you have to expect the slash statement, the closing tag at the end. If it's a deleted terminal, if there were a minus before that statement, then you don't expect the statement, but you still initiate the 4 parallel subparsers. To parse a non-deleted terminal, you have to just expect that very same string in the element content at the current point. Easy. To parse a deleted terminal, you match 0 characters and then insert the string in the parse as if it had been there. To parse an insertion, you expect the characters in the string, but add nothing in the parse. All right. So those are all fairly simple cases. Attributes cause a problem because the content is out of order, because the attribute content appears before the element content. So what you have to do is hold the attributes in abeyance as separate input streams, and then when you come to the @ sign in the grammar, that's when you switch to the input to the content of the attribute with that name. And then you treat all subrules from there as if they've been deleted. So the parsing result of this is, for a serialization like assign with an attribute ID and then an expression where the expression element has been deleted and there's been an insertion of a semicolon at the end, you will get a parse tree at the end of this just like that. In fact, just like the first version with no deletions and no insertions. And then you can just concatenate the element content to give I becomes 0, exactly as in the very simple case earlier on. However, there is a problem that you could get ambiguous parses of the parse tree. And an example is if you had an expression language that allowed you to use different brackets as long as they were matched. For instance, squiggly brackets or round brackets. The problem with this, since the terminals, the brackets have been deleted in the output, is that they will both produce the same parse tree, a term with an expression in it. But you don't know which of those two alternatives produced it. Parsing that serialization back will give you two parses, one with the squiggly brackets inserted and one with the round brackets inserted. So you've got an ambiguous parse. And so just as with serialization, we have to choose one of them. And so in other words, because the serialization deletes information about which brackets in this case were used, we can't always round trip perfectly. We can just get a version of round tripping. Similarly, if you, in the programming language, you deleted all spaces and comments, that's not in the output, so you can't regenerate the original spacing. You can't regenerate the fact that there were comments anywhere. They're just lost in the round tripping. So designing a notation requires a lot to be taken into account simultaneously: usability, functionality, ambiguity. Having an implementation that's easily modifiable during design of the notation is almost essential for good progress. The current pilot implementation, which I'll be using tomorrow in the tutorial, has served well. It works well, but now other implementations are emerging, and so I will be retaining it for future design research. That's not quite the end, because I've got an announcement to make. This moment is the formal announcement of the release of version 1.0 of ixml. Now, I'm hoping that Norm Walsh is online. He said he'd be watching. He's now going to press the button to release the information that it's been released on invisiblexml.org. If you go there, you'll be able to see the final specification, introductory material, pointers to the tutorial, several implementations. We have 3 or 4 implementations that you can use, one in Java, one in Saxon.js, my one, which is a web service, and we have several example grammars for you to have a look for well-known content. And please do come to the tutorial tomorrow. Thank you.
Any question?
Hi, Stephen. Have you ever considered to put the ixml definition language in XML itself? Because I actually find it very weird that something that's called ixml doesn't use an XML input grammar.
It does.
It doesn't.
It does. Whether ixml uses ixml?
No, whether you can write your ixml definition in XML. You can't.
In XML. Oh yeah, you can do that as well. That's permitted. You can just write it straight in XML. Not all the implementations accept XML input, but there are some of them do.
But it's defined somewhere.
Sorry?
The XML is defined for the input.
Absolutely, yeah. In fact, it's the XML form that's the definition of ixml.
Okay, thank you.
I just wanted to point out that not only can you describe the format for XML in XML, ixml in XML, Michael Sperber McQueen has also written a schema for it, so you can also validate it using RelaxNG.
Coffee. Hang on.